supernova is an astronomical event that occurs during the last stages of a massive star's life cycle, marked by a cataclysmic explosion. This explosion results in the sudden, dramatic increase in brightness of the star, sometimes outshining entire galaxies for a short period. The process that leads to a supernova is complex and involves the intricate interplay of nuclear reactions within the star's core. As the star burns through its nuclear fuel, it eventually reaches a point where it can no longer sustain fusion reactions, leading to an inevitable collapse or explosion. Supernovas are classified into different types based on their underlying mechanisms and the spectral lines observed in their light. This classification helps astronomers understand the diverse processes that can lead to these powerful stellar explosions. One of the key characteristics of a supernova is its ability to produce an immense amount of energy in a very short time. This energy release is so intense that it can briefly rival the total output of an entire galaxy. The brightness of a supernova peaks quickly and then fades over weeks to months. During this period, the star sheds its outer layers, dispersing elements throughout space, which plays a critical role in enriching the interstellar medium. Supernovas are significant because they are primary sources of heavy elements in the universe. Elements such as iron, nickel, and gold are synthesized in the extreme conditions of a supernova explosion and are scattered into space, contributing to the cosmic material from which new stars, planets, and even life can form. These stellar explosions also leave behind remnants which can take the form of neutron stars or black holes, depending on the mass of the original star. These remnants are crucial for understanding the extreme states of matter and the fundamental forces of nature. The study of supernovas provides valuable insights into the life cycles of stars, the dynamics of galaxies, and the evolution of the cosmos. Observing supernovas and their remnants allows astronomers to test theories of stellar evolution and the physics of extreme environments. Supernovas have been observed throughout history, with some of the earliest recorded instances dating back to ancient civilizations. These historical observations have helped scientists piece together the frequency and impact of these events over time. In modern times, supernovas are observed using advanced telescopes and detectors that can capture a wide range of electromagnetic radiation, from visible light to gamma rays. These observations have revealed the diverse and complex nature of supernova explosions. The exact mechanisms that trigger supernovas are still an area of active research. While the general processes are understood, the detailed dynamics and variations between different types of supernovas continue to challenge astronomers and astrophysicists. Supernovas also play a role in shaping the structure of galaxies. The shock waves from these explosions can trigger the formation of new stars by compressing nearby gas clouds, thereby influencing the cycle of star formation and evolution within galaxies. The detection of neutrinos and gravitational waves from supernova events has opened new windows into understanding these phenomena. These new forms of observation provide additional information that complements traditional electromagnetic observations. Studying the remnants of supernovas, such as supernova remnants and pulsars, provides clues about the final stages of stellar evolution. These remnants offer a laboratory for studying high-energy physics and the behavior of matter under extreme conditions. Supernovas are also important for understanding the distribution of elements in the universe. By studying the remnants and the elements they produce, astronomers can trace the history of chemical enrichment and the processes that have shaped the cosmos. Throughout history, supernovas have captured the imagination and curiosity of observers. Ancient astronomers documented these bright events, often interpreting them as omens or messages from the gods. One of the most famous historical supernovas is SN 1054, observed by Chinese astronomers in 1054 AD. This event created the Crab Nebula, a prominent feature in modern astronomical studies. European records from the Middle Ages also mention supernovas, although often shrouded in the mysticism and superstition of the time. These observations provide a fascinating glimpse into how different cultures perceived and recorded celestial phenomena. The supernova of 1572, observed by Tycho Brahe, marked a significant milestone in astronomy. Tycho's detailed records challenged the prevailing Aristotelian belief that the heavens were unchanging and perfect. In 1604, Johannes Kepler observed another notable supernova, later named Kepler's supernova. Kepler's meticulous observations further advanced the understanding of stellar explosions and their impact on the cosmos. Supernovas played a crucial role in shifting scientific paradigms, particularly during the Renaissance. These events prompted debates and discussions that gradually led to the acceptance of a dynamic and evolving universe. The 20th century brought a revolution in supernova research with the advent of modern telescopes and photographic techniques. Supernova 1987A, observed in the Large Magellanic Cloud, was a landmark discovery that provided unprecedented insights into the mechanics of supernova explosions. The discovery of supernova remnants in various wavelengths, from radio waves to X-rays, allowed astronomers to study these phenomena long after the initial explosion. These remnants offer a wealth of information about the composition and behavior of supernovae. Historical records from non-Western cultures, such as those in Japan, Korea, and the Middle East, also document supernovas. These accounts contribute to a global understanding of the historical frequency and distribution of supernova events. The interpretation of historical supernova observations often involves translating and analyzing ancient texts and records. This multidisciplinary approach combines astronomy, history, and philology to reconstruct past celestial events. Advancements in technology such as space-based observatories have significantly enhanced our ability to detect and study supernovas. Instruments like the Hubble Space Telescope and the Chandra X-ray Observatory have provided detailed images and data on supernovae and their remnants. Supernovas have also been featured in cultural and literary contexts, reflecting their impact on human thought and imagination. From ancient myths to modern science fiction, these stellar events continue to inspire stories and ideas. The study of historical supernovas helps scientists understand long-term patterns in stellar behavior and galactic evolution. By examining the remnants and records of past supernovas, astronomers can build models to predict future events. Supernovas have played a key role in the development of astrophysics as a discipline. Theoretical frameworks and observational techniques developed to study supernovas have broader applications in the field of astronomy. Today, researchers continue to uncover new supernova events and study historical ones, constantly expanding our knowledge of these powerful explosions. Historical context enriches our understanding, bridging the gap between ancient observations and modern scientific inquiry. Supernovas are crucial in the field of astronomy for several reasons. They provide key insights into the life cycle of stars, illustrating the final stages of stellar evolution. These explosions are also responsible for the creation and dissemination of heavy elements throughout the universe. Elements like iron, gold, and uranium are forged in the intense heat and pressure of a supernova. Studying supernovas helps astronomers understand the dynamics of galaxies. The shock waves from these explosions can trigger the formation of new stars by compressing surrounding gas clouds. Supernovas serve as important cosmic distance markers. Type I supernovas, in particular, have a consistent luminosity, making them reliable standard candles for measuring astronomical distances. These stellar events also offer a natural laboratory for studying high-energy physics. The extreme conditions present in a supernova provide a unique environment to observe and test theories about nuclear reactions and particle interactions. The remnants of supernovas, such as neutron stars and black holes, are of great interest to astronomers. These objects help scientists explore the limits of matter and the nature of gravity. Observing supernovas in other galaxies allows astronomers to compare different galactic environments. This comparative study helps us understand the diverse conditions that can lead to supernova explosions. Supernovas contribute to the interstellar medium by enriching it with newly formed elements. This enrichment is essential for the chemical complexity necessary for the formation of planets and, ultimately, life. The light curves and spectra of supernovas provide detailed information about the explosion mechanisms. By analyzing these data, astronomers can infer the physical properties of the progenitor stars and the explosion dynamics. Supernovas also play a role in the feedback processes within galaxies. The energy and material ejected by these explosions can influence the formation and evolution of stars and planetary systems. The detection of neutrinos from supernovas has opened new avenues for research. These nearly massless particles provide additional information about the core collapse process and the conditions within the star's core. Gravitational waves generated by supernova events offer another dimension of observational data. These waves help scientists study the violent and dynamic processes occurring during the explosion. The impact of supernovas on cosmic rays is another area of study. These high-energy particles, accelerated by supernova shockwaves, contribute to our understanding of particle physics and the interstellar medium. Supernovas also have a significant influence on the structure of galaxies. The distribution of supernova remnants helps map out regions of active star formation and the life cycle of stellar populations. Overall, supernovas are integral to our understanding of the universe. They bridge the gap between stellar astrophysics, galactic dynamics, and cosmology, providing a comprehensive view of the cosmos. In this video, we'll delve into the fascinating world of supernovas, exploring their origins, types, and significance in the cosmos. We'll begin by understanding what a supernova is and why these stellar explosions are crucial to astronomy. Next, we'll categorize the different types of supernovas, focusing on their distinct characteristics and what sets them apart. We'll look at Type I and Type II supernovas, breaking down the subtypes and their unique properties. We'll then journey through the life cycle of a star, leading up to the dramatic finale of a supernova explosion. Understanding this life cycle is key to grasping how and why stars end their lives in such spectacular fashion. Following that, we'll dive into the specifics of Type I supernovas, which typically involve white dwarf stars. We'll explore the conditions that lead to their explosive fate and what happens during these cataclysmic events. Then we'll switch gears to Type II supernovas, focusing on massive stars and their core collapse. We'll explain the processes that drive these powerful explosions and what remains after the dust settles. The role of neutrinos in supernovas is a fascinating topic, and we'll discuss how these elusive particles are produced and what they tell us about the internal workings of a star just before it explodes. Observing supernovas has always been a challenge and a thrill for astronomers. We'll cover the history of supernova observations, from ancient records to modern telescopic discoveries, and what these observations have taught us. Supernovas are not just spectacular light shows, they're also cosmic forges that create and disperse elements across the universe. We'll delve into the process of nucleosynthesis and the creation of elements during a supernova explosion. We'll also examine the impact of supernovas on different galaxies, looking at how these events shape and influence galactic environments and the birth of new stars. The aftermath of a supernova is as intriguing as the explosion itself. We'll discuss the formation of neutron stars, black holes, and supernova remnants, and their significance in the universe. Theoretical models and simulations have advanced our understanding of supernovas. We'll explore the cutting-edge research and the latest theories that help explain these stellar phenomena. Historical context adds depth to our understanding, and we'll look back at how supernovas have been perceived and recorded throughout history, from ancient civilizations to modern science. Supernovas also serve as important tools in astronomy, acting as standard candles for measuring cosmic distances and helping us map the universe's expansion. We'll discuss their role in these crucial measurements. We'll touch on the detection of gravitational waves from supernova events, a relatively new field that provides additional insights into these explosive phenomena and the extreme conditions they create. Finally, we'll wrap up this section with a look at the ongoing research and future prospects in the study of supernovas, highlighting the exciting discoveries yet to come in this ever-evolving field. Type I supernovas are a fascinating class of stellar explosions that typically involve white dwarf stars. These supernovas occur in binary systems, where a white dwarf star pulls material from its companion star. As the white dwarf accumulates material, it reaches a critical mass known as the Chandrasekhar limit. This limit is approximately 1.4 times the mass of our Sun. Beyond this point, the white dwarf can no longer support itself against gravitational collapse. The collapse triggers a runaway thermonuclear reaction. This reaction is so powerful that it completely disrupts the white dwarf, leading to a dramatic and bright explosion visible across vast distances. Type I supernovas are further classified into subtypes, such as Type Ia, Type Ib, and Type X. Type Ia supernovas are the most well-known and have a consistent peak brightness, making them valuable as standard candles in measuring cosmic distances. Type Ib and X supernovas, on the other hand, involve massive stars that have lost their outer hydrogen layers before the explosion. These types differ in the presence or absence of helium lines in their spectra. The consistent luminosity of Type I supernovas is due to the uniformity in the amount of material that explodes. This property allows astronomers to use them to measure distances to faraway galaxies with great precision. The light curve of a Type I supernova, which shows how its brightness changes over time, follows a distinctive pattern. This pattern helps astronomers identify these events and study their properties in detail. Spectral analysis of Type I supernovas reveals the presence of heavy elements like iron and nickel. These elements are synthesized during the explosion and provide clues about the processes happening within the supernova. Type I supernovas play a critical role in enriching the interstellar medium with heavy elements. The materials ejected during the explosion contribute to the formation of new stars and planets. These supernovas also influence the dynamics of their host galaxies. The energy released can trigger star formation in surrounding gas clouds, adding to the cycle of stellar birth and death. Type I supernovas have also been key in understanding the expansion of the universe. Observations of distant Type I supernovas led to the discovery of dark energy, a mysterious force driving the acceleration of the universe's expansion. Despite their importance, many aspects of Type I supernovas remain a mystery. Ongoing research aims to better understand the progenitor systems and the exact mechanisms that lead to these powerful explosions. Advanced telescopes and observational techniques continue to uncover new Type I supernova events. Each discovery provides additional data that helps refine our models and theories about these stellar phenomena. The study of Type I supernovas also benefits from simulations and theoretical work. Researchers use complex models to simulate the conditions leading up to and following the explosion, offering deeper insights into these events. Type I supernovas remain a vibrant area of research in astrophysics. Their significance spans from understanding stellar evolution and nucleosynthesis to probing the fundamental nature of the cosmos itself. Type II. Supernovas are a spectacular class of stellar explosions that occur in massive stars. These stars have at least 8 times the mass of our Sun and end their lives in a dramatic collapse and explosion. The process begins when the star exhausts its nuclear fuel. Without the pressure from nuclear fusion to counteract gravity, the core collapses under its own weight, forming a dense neutron star or black hole. As the core collapses, the outer layers of the star fall inward, generating an immense amount of energy. This energy creates a powerful shock wave that propagates outward, causing the outer layers to explode. Type II supernovas are characterized by the presence of hydrogen lines in their spectra. This distinguishes them from other types of supernovas, as they retain their hydrogen envelopes until the explosion. The light curve of a Type II supernova typically shows a plateau phase. During this phase, the brightness remains relatively constant for a period before gradually fading, indicating the sustained energy release from the explosion. These supernovas can leave behind neutron stars, which are incredibly dense remnants composed mostly of neutrons. In some cases, if the collapsing core is massive enough, it can form a black hole. The energy released in a Type II supernova is staggering, often outshining entire galaxies for a brief period. This energy is a result of the rapid release of gravitational potential energy as the core collapses. Type II supernovas play a crucial role in the cosmos by dispersing heavy elements into space. Elements such as oxygen, carbon, and iron are synthesized in the core and expelled into the interstellar medium. The shock waves from these explosions can trigger the formation of new stars. By compressing nearby gas clouds, they initiate the process of star formation, contributing to the ongoing cycle of stellar evolution. Observations of Type II supernovas provide valuable data on the late stages of stellar evolution. By studying these explosions, astronomers gain insights into the life cycles of massive stars and the conditions leading to core collapse. Type II supernovas are also important for understanding the structure and dynamics of galaxies. The energy and material they release influence the interstellar medium and the overall evolution of their host galaxies. The study of neutrinos emitted during a Type II supernova has provided crucial information about the core collapse process. Neutrinos are elusive particles that carry away a significant portion of the energy released during the explosion. Gravitational waves from Type II supernovas offer another window into these events. These waves, ripples in space-time caused by the violent core collapse, provide additional data on the explosion mechanics and the properties of the progenitor star. Research into Type II supernovas involves both observations and theoretical models. Advanced simulations help scientists understand the complex physics of core collapse and the subsequent explosion. Type II supernovas remain a vibrant field of study in astrophysics. They are key to unlocking the mysteries of stellar death, the creation of elements, and the dynamic processes shaping galaxies. Type I supernovas are divided into several subcategories, each with unique characteristics. These subcategories help astronomers identify the specific nature and origin of the explosion. Type Ia supernovas are the most well-known and occur in binary systems where a white dwarf accretes material from a companion star. This process leads to a runaway thermonuclear reaction. Type Ib supernovas, on the other hand, arise from massive stars that have lost their outer hydrogen layers. This loss occurs through strong stellar winds or interaction with a companion star. Type Ik supernovas are similar to Type Ib, but have also lost their helium layers. The progenitor stars of Type Ik supernovas are often stripped to their core, resulting in a different spectral signature. The key distinguishing feature of Type Ia supernovas is the absence of hydrogen and helium lines in their spectra. This absence points to the white dwarf origin and the unique explosion mechanism. Type Ib and Ik supernovas are collectively known as stripped envelope supernovas. They provide crucial insights into the lives of massive stars and the processes that strip away their outer layers. One of the main uses of Type Ia supernovas is as standard candles in cosmology. Their consistent peak luminosity allows for accurate distance measurements across vast cosmic scales. Type Ib and Ik supernovas, while less uniform than Type Ia, still offer valuable information about stellar evolution. They help astronomers understand the end stages of massive stars and the role of binary interactions. The spectral differences between these subcategories are critical for identification. By analyzing the spectra, astronomers can determine the specific type of supernova and gather information about the progenitor star. The light curves of Type Ia, Ib, and Ik supernovas also show distinct patterns. Type Ia supernovas have a characteristic peak and decline, while the light curves of Ib and Ik can vary more due to their diverse progenitor systems. Type Ia supernovas are often found in older stellar populations, such as elliptical galaxies. This distribution reflects their origin from long-lived white dwarfs in binary systems. Type Ib and Ik supernovas are more commonly found in regions of active star formation. These environments are rich with massive stars that can end their lives in such explosive events. The study of these subcategories extends to their remnants. Type Ia supernovas typically leave no core remnant, while Type Ib and Iks can leave behind neutron stars or black holes. Understanding the differences between these subcategories helps astronomers build a more complete picture of stellar death. Each type provides unique clues about the processes leading up to and following the explosion. Research into Type I supernova subcategories continues to evolve with new observations and theoretical models. Each discovery adds to our knowledge of the diverse ways stars can end their lives. By studying the subcategories of Type I supernovas, astronomers gain deeper insights into the complexities of stellar evolution and the dynamic processes that shape our universe. Type II supernovas are classified into several subcategories, each with distinctive features. These classifications help astronomers understand the diversity of explosions and their progenitor stars. Type IIp supernovas are the most common subtype. The P stands for plateau, which describes the flat section in their light curves where brightness remains steady for an extended period. Type IIL supernovas are characterized by a linear decline in their light curves. Unlike Type IIp, the brightness of Type IIL supernovas decreases steadily after the initial peak. Type II in supernovas are notable for their narrow spectral lines. The N signifies the interaction with a dense circumstellar medium, leading to unique emission features. Type IIb supernovas exhibit a combination of Type II and Type Ib characteristics. They show hydrogen lines early on, but these lines diminish revealing features typical of Type Ib supernovas. The progenitor stars of Type IIp supernovas are typically red supergiants. These stars have extended outer envelopes, which contribute to the plateau phase observed in their light curves. Type IIL supernovas usually arise from more compact progenitor stars. These stars have lost a significant portion of their hydrogen envelopes, resulting in the linear decline of brightness. For Type II supernovas, the progenitors are often surrounded by a dense shell of material. This material interacts with the supernova ejecta, producing the characteristic narrow spectral lines. Type IIb supernovas are thought to originate from binary systems, where the progenitor star has lost much of its hydrogen envelope due to interaction with a companion star. The study of Type IIp supernovas provides insights into the late stages of red supergiant stars. These explosions help astronomers understand how massive stars evolve and end their lives. Observations of Type IIL supernovas shed light on the processes that strip stars of their outer layers. This knowledge is crucial for understanding the diversity of stellar deaths. Type II supernovas offer a glimpse into the environments around massive stars. The interaction with circumstellar material reveals information about the mass loss history of the progenitor star. Type IIb supernovas bridge the gap between hydrogen-rich and hydrogen-poor supernovas. Studying these events helps astronomers understand the transitional phases in stellar evolution. The light curves and spectra of these subcategories provide important clues about the explosion mechanisms. Each subtype has distinct features that reflect the conditions of the progenitor stars and their environments. Research into Type II supernova subcategories continues to advance, with new observational data and theoretical models. Each discovery contributes to a more comprehensive understanding of stellar explosions and their aftermath. By examining the subcategories of Type II supernovas, astronomers gain valuable insights into the diverse and dynamic processes that govern the life cycles of massive stars and the complex phenomena that occur at the end of their lives. Comparing Type I and Type II supernovas reveals significant differences in their progenitors and explosion mechanisms. Type I supernovas generally involve white dwarf stars in binary systems, while Type II supernovas result from the core collapse of massive stars. Type Ia supernovas, a subtype of Type I, are known for their consistent peak luminosity. This uniformity makes them valuable standard candles for measuring cosmic distances. In contrast, Type II supernovas exhibit a range of brightness levels and decay rates, reflecting the diversity of their progenitor stars. The spectra of Type I and Type II supernovas also differ markedly. Type I supernovas lack hydrogen lines, indicating the absence of hydrogen in their progenitor systems. Type II supernovas, on the other hand, prominently display hydrogen lines, as they explode while still retaining their hydrogen envelopes. Light curves provide another point of comparison. Type Ia supernovas show a sharp peak followed by a gradual decline, while Type II supernovas, especially Type IIp, exhibit a plateau phase where brightness remains relatively constant before fading. The remnants left behind by these supernovas are also distinct. Type Ia supernovas typically leave no central remnant, as the white dwarf is completely disrupted. Type II supernovas often leave behind neutron stars or black holes, depending on the mass of the progenitor star. Neutrino emissions are significant in Type II supernovas due to the core collapse process. These neutrinos carry away a large amount of energy and provide crucial insights into the explosion mechanism. In contrast, Type I supernovas produce fewer neutrinos, as their explosion mechanism is thermonuclear rather than gravitational collapse. Gravitational waves are expected from both types of supernovas, but the signals differ. Type II supernovas, with their core collapse and formation of neutron stars or black holes, generate stronger and more detectable gravitational waves compared to Type I supernovas. The environments in which these supernovas occur also vary. Type Ia supernovas can be found in both young and old stellar populations, reflecting their origin in binary systems with white dwarfs. Type II supernovas are predominantly found in regions of active star formation, where massive stars are more common. Chemical enrichment of the interstellar medium is another area of distinction. Type Ia supernovas contribute significantly to the production of iron peak elements, while Type II supernovas are major producers of alpha elements like oxygen and silicon. The progenitor systems of Type I and Type II supernovas influence the galactic environments differently. Type Ia supernovas, being older, contribute to the chemical evolution over longer timescales, while Type II supernovas have a more immediate impact on star-forming regions. In terms of frequency, Type II supernovas are more common in the universe than Type Ia supernovas. This is because massive stars, which produce Type II supernovas, have shorter lifespans and thus explode more frequently than the binary systems that lead to Type Ia supernovas. Type I supernovas, particularly Type Ia, are critical for cosmology. Their use as standard candles has led to the discovery of the accelerating expansion of the universe, a breakthrough that has profound implications for our understanding of dark energy. Type II supernovas, with their diverse subtypes, provide rich information about stellar evolution and the life cycles of massive stars. Each subtype offers unique insights into the different stages of stellar death and the processes that lead to supernova explosions. Both types of supernovas play essential roles in galactic ecology. They drive the cycle of star formation and death, distribute heavy elements, and influence the dynamics of galaxies through their powerful explosions and subsequent remnants. The ongoing study and comparison of Type I and Type II supernovas continue to enhance our understanding of the universe. Each type, with its unique characteristics and contributions, helps piece together the complex puzzle of stellar and galactic evolution. Stellar formation begins within vast clouds of gas and dust, known as molecular clouds or stellar nurseries. These regions are cold and dense, providing the perfect conditions for new stars to form. The process starts when a disturbance, such as a nearby supernova explosion or the collision of two molecular clouds, compresses parts of the cloud. This compression leads to the formation of dense clumps within the cloud. As these clumps collapse under their own gravity, they begin to heat up and form protostars. A protostar is a very young star still in the process of gathering mass from its parent molecular cloud. During this collapse, the material in the cloud begins to spin, forming a rotating disk around the protostar. This disk is called a protoplanetary disk, and it's where planets, asteroids, and other objects can eventually form. The core of the protostar continues to contract and heat up. When the temperature and pressure at the core become high enough, nuclear fusion ignites, and the protostar becomes a main sequence star. Nuclear fusion is the process that powers stars, where hydrogen atoms combine to form helium, releasing enormous amounts of energy. This energy creates an outward pressure that balances the inward pull of gravity. Once nuclear fusion begins, the star enters a long period of stability known as the main sequence phase. During this time, the star steadily fuses hydrogen into helium in its core, producing light and heat. The length of time a star spends on the main sequence depends on its mass. Massive stars burn through their fuel quickly and have shorter lifespans, while smaller stars can remain on the main sequence for billions of years. Stars do not form in isolation. Often, multiple stars form from the same molecular cloud, creating star clusters. These clusters can range from a few dozen to thousands of stars, bound together by gravity. As stars form, they also influence their surroundings. The intense radiation and stellar winds from young stars can erode the molecular cloud, dispersing the gas and dust, and sometimes triggering the formation of new stars. Some regions within molecular clouds may not form stars. Instead, they remain as cold, dark nebulae, which can be observed as dark patches against the brighter background of the Milky Way or other galaxies. The initial mass function describes the distribution of star masses that form in a molecular cloud. Most stars are relatively low mass, with massive stars being much rarer. Star formation is an ongoing process throughout the universe. New stars are continuously born in galaxies, replenishing the stellar population and contributing to the dynamic evolution of galaxies. The study of stellar formation provides critical insights into the early stages of star life and the conditions that lead to the birth of stars. Observing star-forming regions with telescopes, especially those that capture infrared and radio wavelengths, allows astronomers to peer into these dense clouds and uncover the secrets of star formation. Understanding stellar formation helps us grasp the broader picture of cosmic evolution, from the birth of individual stars to the development of galaxies and the universe as a whole. This knowledge also informs our understanding of the origins of our own solar system and the potential for star formation in other parts of the cosmos. The main sequence phase is the longest and most stable period in a star's life cycle. During this phase, a star fuses hydrogen into helium in its core, producing energy that balances the gravitational forces pulling the star inward. Stars on the main sequence are classified based on their mass and temperature, which determine their color and brightness. Massive hot stars are blue or white, while smaller, cooler stars appear yellow, orange or red. The position of a star on the Hertzsprung-Russell diagram during the main sequence phase is determined by its mass. More massive stars are located in the upper left of the diagram, while less massive stars are found in the lower right. A star's mass is the primary factor that dictates its main sequence lifespan. Massive stars burn through their hydrogen fuel much more quickly than smaller stars, resulting in shorter lifespans of only a few million years. In contrast, smaller stars, like red dwarfs, can remain on the main sequence for tens of billions of years. Our Sun, a medium-sized star, will spend about 10 billion years on the main sequence. During the main sequence phase, a star maintains a stable equilibrium. The energy produced by nuclear fusion generates an outward pressure that counteracts the inward pull of gravity, keeping the star stable. The core of a main sequence star is where hydrogen fusion occurs. The temperatures in the core can reach millions of degrees, allowing hydrogen nuclei to overcome their repulsive forces and combine to form helium. As hydrogen fuses into helium, energy is released in the form of light and heat. This energy radiates outward from the core, eventually reaching the star's surface and shining into space. In addition to producing energy, the fusion process gradually changes the composition of the star's core. Over time, the core becomes enriched with helium, while the outer layers remain mostly hydrogen. Stars on the main sequence are relatively stable, but they can still exhibit various types of variability. Some stars, known as variable stars, experience changes in brightness due to pulsations or interactions with a companion star. The main sequence phase is also a time of significant stellar wind. This wind, composed of charged particles, streams away from the star and can influence the star's surroundings, including the formation of planetary systems. Stars like the Sun can have solar flares and coronal mass ejections during their main sequence phase. These events release large amounts of energy and charged particles, which can impact planets and other objects in the star's vicinity. As a star exhausts its hydrogen fuel, the balance between pressure and gravity begins to shift. The core contracts and heats up, eventually leading to the star's evolution into the next phase of its life cycle. For a star like the Sun, this transition will lead to the red giant phase, where the outer layers expand and the core begins to fuse helium into heavier elements. For more massive stars, the transition can lead to more dramatic changes, culminating in supernova explosions. Understanding the main sequence phase is crucial for comprehending the broader processes of stellar evolution. This stable period forms the foundation for the life cycles of stars and the dynamics of galaxies. The main sequence phase provides insights into the conditions necessary for the development of planetary systems and, potentially, the emergence of life. As a star exhausts its hydrogen fuel, it leaves the main sequence and enters the red giant or supergiant phase. This phase marks a period of dramatic change in the star's structure and appearance. In the red giant phase, the core contracts and heats up while the outer layers expand and cool. This causes the star to swell many times its original size, becoming much larger and brighter. For medium-sized stars like our Sun, this expansion results in the red giant phase. The star's surface cools, giving it a reddish hue, while its luminosity increases significantly. In more massive stars, this phase leads to the formation of supergiants. These stars become even larger and more luminous, with surface temperatures varying depending on their mass and composition. During the red giant phase, the core temperature rises until it becomes hot enough to fuse helium into carbon and oxygen. This helium fusion process occurs in a shell around the core, creating a layered structure. The fusion of helium is less stable than hydrogen fusion, leading to periodic outbursts or pulses. These thermal pulses cause the star's outer layers to expand and contract, sometimes shedding material into space. For red giants, the loss of mass through stellar winds becomes significant. These winds carry away the star's outer layers, contributing to the enrichment of the interstellar medium with heavier elements. The red giant phase is relatively short-lived compared to the main sequence. For a star like the Sun, it lasts only a few 100 million years, a brief period in the star's overall life cycle. In supergiants, the changes are even more pronounced. The core contracts and heats up further, leading to successive stages of fusion, where heavier elements like neon, magnesium, and silicon are created. The outer layers of supergiants can become extremely tenuous, leading to complex and often beautiful structures in the surrounding space. These structures are sometimes visible as nebulae, illuminated by the star's intense radiation. The end of the red giant or supergiant phase depends on the star's mass. For red giants, the core eventually becomes a dense, inert remnant called a white dwarf, while the outer layers are expelled to form a planetary nebula. In the case of supergiants, the process culminates in a core collapse supernova. The intense gravitational forces cause the core to collapse rapidly, resulting in a catastrophic explosion that can outshine entire galaxies. The remnants of supergiant stars can be neutron stars or black holes, depending on the mass of the core left after the explosion. These remnants are incredibly dense and have powerful gravitational fields. Observing red giants and supergiants helps astronomers understand the late stages of stellar evolution. The changes these stars undergo provide insights into the processes that lead to their ultimate fate. The red giant and supergiant phases highlight the dynamic and ever-changing nature of stars. From their quiet beginnings in molecular clouds to their explosive ends, stars continuously shape and enrich the universe. Understanding these phases is crucial for a comprehensive view of the life cycles of stars and the cosmic processes that depend on them. Core collapse marks the final stage in the life of a massive star. When a star's core can no longer sustain fusion reactions, it succumbs to the relentless pull of gravity. As the core contracts, temperatures and pressures skyrocket. These extreme conditions trigger the fusion of heavier elements, leading to the production of iron in the core. Iron fusion does not release energy. Instead, it consumes energy, causing the core to become inert and unable to support the weight of the star's outer layers. With no fusion to counteract gravity, the core collapses in a fraction of a second. This collapse is rapid and catastrophic, causing the core to shrink to a fraction of its original size. The collapsing core reaches incredible densities, comparable to an atomic nucleus. This density forces protons and electrons to combine, forming neutrons and releasing a flood of neutrinos. Neutrinos play a crucial role during core collapse, carrying away vast amounts of energy. These particles escape from the core, taking with them the thermal energy that had previously supported the star. The sudden halt of the core's collapse generates a powerful shock wave. This shock wave travels outward, colliding with the infalling outer layers of the star. As the shock wave propagates, it gains energy from the rebounding core and the neutrinos flooding outwards. This energizes the shock wave, allowing it to blast through the star's outer layers. The interaction of the shock wave with the star's outer layers results in the supernova explosion. This explosion is so intense that it can outshine the entire host galaxy for a short period. The expelled material from the explosion enriches the surrounding space with heavy elements. This process of nucleosynthesis in supernovas is crucial for the chemical evolution of the universe. Depending on the mass of the original star, the remnants of the core collapse can form a neutron star or a black hole. Neutron stars are incredibly dense, while black holes have gravitational fields so strong that not even light can escape. Neutron stars often manifest as pulsars, emitting beams of radiation that sweep across space like lighthouse beacons. These objects provide valuable insights into the properties of matter under extreme conditions. Black holes, with their intense gravitational pull, profoundly influence their surroundings. They can accrete matter from nearby stars and emit powerful jets of energy, impacting their galactic environment. The study of core collapse supernovas provides critical information about the life cycles of massive stars. By observing these events, astronomers can test theories of stellar evolution and the behavior of matter at extreme densities. Understanding core collapse is also essential for exploring the origins of elements and the dynamics of galaxies. These explosive events play a pivotal role in shaping the universe, influencing the formation of new stars and planets. Through ongoing research and observation, scientists continue to unravel the complexities of core collapse and its profound effects on the cosmos. The core collapse of a massive star is the crucial process that initiates a supernova. Without the collapse, the explosive energy needed for a supernova would not be generated. As the core collapses, it reaches extreme densities and temperatures. These conditions are necessary for the production of heavy elements through nuclear reactions. The collapse also leads to the formation of a neutron star or black hole at the core. This remnant is a key outcome of the supernova event, influencing the surrounding space. Neutrinos play a significant role during the core collapse, carrying away energy and facilitating the explosion. The sudden release of neutrinos helps drive the shockwave outward. The shockwave generated by the core collapse is the force that disrupts the star's outer layers. This wave must be strong enough to overcome the gravitational pull holding the star together. The energy from the core collapse and the subsequent shockwave is immense. This energy is what powers the supernova, allowing it to shine with incredible brightness. Core collapse sets off a chain of nuclear reactions in the star's outer layers. These reactions produce a variety of elements, enriching the interstellar medium with new material. The interaction of the shockwave with the outer layers creates complex structures within the expanding supernova remnant. These structures can be observed long after the initial explosion. The development of the supernova depends on the mass and composition of the progenitor star. Different types of core collapse supernovas result from different initial conditions. The formation of neutron stars or black holes during core collapse significantly impacts the evolution of the supernova remnant. These dense objects can influence nearby matter and radiation. The distribution of elements created during the core collapse and explosion is crucial for galactic evolution. These elements form the building blocks of new stars and planets. The energy released during the core collapse also affects the surrounding environment. Shock waves from supernovas can trigger the formation of new stars by compressing nearby gas clouds. The study of core collapse and its role in supernova development helps astronomers understand the life cycles of massive stars. Each supernova provides valuable data on these catastrophic events. Observations of supernovas in different stages of development reveal details about the explosion mechanics. By studying these stages, scientists can piece together the processes occurring during and after the core collapse. Understanding the role of core collapse in supernova development is essential for a comprehensive view of stellar evolution. This knowledge sheds light on the origins of elements and the dynamic processes shaping galaxies and the universe as a whole. The accretion process plays a vital role in the formation and evolution of many astronomical objects. It involves the accumulation of material onto a celestial body, significantly impacting its growth and behavior. In the context of supernovas, accretion is crucial in Type Ia supernovas. Here, a white dwarf star in a binary system gains material from its companion star, eventually leading to a runaway nuclear reaction. The material is transferred through an accretion disk, a rotating disk of gas and dust formed around the white dwarf. The disk is created by the angular momentum of the infalling matter, which spirals inward over time. As material accumulates onto the white dwarf, it compresses and heats up. When the pressure and temperature become high enough, nuclear fusion reactions can ignite, leading to a dramatic increase in brightness. In Type Ia supernovas, the white dwarf reaches the Chandrasekhar limit, approximately 1.4 times the mass of the Sun. Beyond this limit, the white dwarf can no longer support itself against gravitational collapse, triggering a thermonuclear explosion. The accretion process is not limited to supernovas. It is also essential in the growth of black holes and neutron stars. These objects can accrete matter from their surroundings or from a companion star in a binary system. Accretion disks around black holes and neutron stars are sites of intense energy release. The gravitational potential energy of the infalling material is converted into radiation, often observed as X-rays. The efficiency of accretion in converting mass to energy is very high, especially near black holes. This efficiency makes accretion disks some of the most luminous objects in the universe. Accretion also plays a role in the formation of planetary systems. Protoplanetary disks around young stars are the birthplaces of planets, formed from the dust and gas that accrete onto them. The dynamics of accretion disks are complex, involving turbulence, magnetic fields, and angular momentum transfer. These processes determine the rate at which material accretes and the eventual fate of the central object. In binary systems, the transfer of material through accretion can lead to various phenomena, such as X-ray binaries and cataclysmic variable stars. These systems provide valuable insights into the behavior of matter under extreme conditions. The study of accretion processes helps astronomers understand a wide range of astrophysical phenomena, from the growth of supermassive black holes in the centers of galaxies to the formation of stars and planets in stellar nurseries. Observations of accretion disks in different wavelengths, from radio to X-rays, reveal the complex interplay of forces shaping these structures. These observations help refine theoretical models of accretion. Understanding the accretion process is crucial for piecing together the life cycles of stars and the evolution of galaxies. It provides a framework for interpreting the energetic phenomena observed in the universe. The accretion process is a key mechanism driving the growth and evolution of many astronomical objects. Its study continues to advance our knowledge of the cosmos, revealing the underlying physics of some of the most dynamic and energetic events in the universe. The Chandrasekhar limit is a fundamental concept in astrophysics, defining the maximum mass that a white dwarf star can have while remaining stable. This limit is approximately 1.4 times the mass of our Sun. The limit is named after Subramanian Chandrasekhar, the Indian-American astrophysicist who first calculated it in the 1930s. His work provided critical insights into the fate of stars and the formation of different stellar remnants. White dwarfs are the remnants of stars that were not massive enough to end their lives in a supernova. They are incredibly dense, with their matter compressed to a state where electron degeneracy pressure supports them against gravitational collapse. Electron degeneracy pressure arises from the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. This pressure provides the force needed to counteract gravity in white dwarfs. However, this support has a limit. When the mass of a white dwarf approaches the Chandrasekhar limit, the electron degeneracy pressure can no longer sustain the star against its own gravity. As a white dwarf nears the Chandrasekhar limit, it becomes increasingly unstable. If it gains mass, for example, through accretion from a companion star, it can reach the critical point where collapse becomes inevitable. Upon reaching the Chandrasekhar limit, the white dwarf undergoes a catastrophic collapse. This collapse leads to a runaway thermonuclear reaction, resulting in a Type Ia supernova explosion. Type Ia supernovas are crucial for cosmology because their consistent peak luminosity allows astronomers to use them as standard candles. This helps measure distances in the universe and study its expansion. The concept of the Chandrasekhar limit also explains why some white dwarfs do not explode as supernovas. Those with masses below the limit remain stable, slowly cooling and fading over billions of years. In addition to white dwarfs, the Chandrasekhar limit plays a role in the formation of neutron stars. If the remnant core of a star after a supernova is below this limit, it can become a neutron star supported by neutron degeneracy pressure. Chandrasekhar's work on this limit revolutionized our understanding of stellar evolution. It provided a clear demarcation between different types of stellar remnants and their respective end states. The calculation of the Chandrasekhar limit involves complex physics, including general relativity and quantum mechanics. It stands as a testament to the power of theoretical physics in explaining astronomical phenomena. Observations of white dwarfs in binary systems provide empirical support for the Chandrasekhar limit. When these stars accumulate mass and approach the limit, their behavior aligns with Chandrasekhar's predictions. Understanding the Chandrasekhar limit helps explain the diversity of supernova types and their progenitors. It clarifies why only certain white dwarfs can lead to Type Ia supernovas, while others remain stable. The Chandrasekhar limit remains a cornerstone of astrophysics, bridging the gap between theoretical predictions and observational evidence. It continues to guide our exploration of stellar remnants and the dynamic processes governing their evolution. Carbon-oxygen fusion is a critical process in the life cycle of massive stars. It occurs after the star has exhausted its helium fuel and its core temperature and pressure rise to extreme levels. In stars much larger than our Sun, once helium is depleted, the core contracts further, heating up to temperatures exceeding 600 million degrees Celsius. At these temperatures, carbon and oxygen nuclei can overcome their repulsive forces and begin to fuse. Carbon fusion results in the creation of heavier elements such as neon, sodium, and magnesium. This process releases a tremendous amount of energy, temporarily supporting the star against gravitational collapse. Oxygen fusion occurs at even higher temperatures and leads to the formation of silicon, sulfur, and phosphorus. These reactions also produce energy, continuing to fuel the star's core. The fusion of carbon and oxygen in a star's core is a complex series of reactions. Each reaction pathway involves multiple steps and intermediate products, contributing to the buildup of heavier elements. During carbon-oxygen fusion, the star's core becomes layered, with different fusion processes occurring at various depths. This stratification resembles an onion, with each layer fusing different elements. The energy generated by carbon-oxygen fusion causes the outer layers of the star to expand. This expansion can result in the star becoming a red supergiant, with a vastly increased radius and luminosity. The advanced stages of carbon-oxygen fusion signal the final phases of a massive star's life. As fusion progresses, the core contracts and heats up, setting the stage for the ultimate collapse and explosion. Fusion reactions involving carbon and oxygen also produce neutrinos. These nearly massless particles escape the star, carrying away energy and providing insights into the core processes through neutrino detection experiments. Carbon-oxygen fusion is highly sensitive to temperature changes. Small increases in core temperature can significantly accelerate the fusion rate, leading to dynamic and sometimes unstable conditions within the star. The fusion of carbon and oxygen creates the conditions necessary for the next stage of stellar evolution, silicon burning. This subsequent phase leads to the formation of iron, marking the end of the star's ability to sustain fusion. Once iron is formed in the core, fusion ceases to produce net energy, as iron fusion consumes more energy than it releases. This sets the stage for the catastrophic core collapse of the star. Understanding carbon-oxygen fusion is crucial for explaining the life cycles of massive stars and the elements they produce. These processes contribute to the chemical enrichment of the universe, seeding future generations of stars and planets. Observations of supernova remnants and the distribution of elements in the universe provide evidence of past carbon-oxygen fusion in massive stars. These remnants offer a snapshot of the final moments before a star's explosive end. The study of carbon-oxygen fusion helps astronomers piece together the complex puzzle of stellar evolution. It reveals the intricate interplay of nuclear physics and stellar dynamics that govern the life and death of stars. A runaway thermonuclear reaction is a critical event in the life of a star that can lead to a dramatic explosion. This reaction occurs when nuclear fusion processes accelerate uncontrollably, releasing vast amounts of energy in a short period. In the context of Type I supernovas, this runaway reaction begins in a white dwarf star. As the white dwarf accretes material from a companion star, it approaches the Chandrasekhar limit, increasing its core temperature and pressure. Once the core conditions are right, carbon fusion ignites explosively. Unlike stable fusion, which occurs gradually, a runaway reaction happens almost instantaneously, causing a massive release of energy. This sudden burst of fusion rapidly heats the surrounding material, leading to further fusion reactions in a chain reaction. The entire star is engulfed in a thermonuclear fireball within seconds. The energy released by the runaway thermonuclear reaction is so immense that it overcomes the gravitational binding energy of the white dwarf. This causes the star to blow apart in a supernova explosion. Runaway thermonuclear reactions are characterized by the rapid production of heavy elements. These elements are synthesized in the extreme temperatures and pressures created by the explosion. The reaction releases an enormous amount of light and heat, making Type I supernovas some of the brightest events in the universe. They can outshine entire galaxies for weeks or months. The process also produces a significant amount of neutrinos. These particles escape from the explosion almost immediately, providing a burst of neutrinos that can be detected by observatories on Earth. Runaway thermonuclear reactions are not limited to white dwarfs. They can also occur in massive stars during their final stages, contributing to the explosive power of core collapse supernovas. The speed and intensity of a runaway thermonuclear reaction leave no time for equilibrium processes to stabilize the star. This lack of control leads to the complete disruption of the star. In Type I supernovas, the runaway reaction spreads from the core outward. This outward propagation ensures that the entire star participates in the explosion, leading to the ejection of its outer layers. Runaway thermonuclear reactions are crucial for understanding the diversity of supernovae. They explain why Type I supernovas have such uniform brightness, as the process is driven by well-understood physical principles. The study of these reactions provides insights into nuclear physics under extreme conditions. It helps scientists understand how elements are forged in the most violent environments in the universe. By observing the light curves and spectra of supernovas, astronomers can infer details about the runaway thermonuclear reactions that power them. These observations help refine models of stellar explosions. Understanding runaway thermonuclear reactions enhances our knowledge of stellar evolution and the life cycles of stars. It sheds light on the processes that lead to the creation of the elements and the dynamic events that shape the cosmos. The final explosion of a supernova is one of the most energetic events in the universe. This cataclysmic explosion marks the end of a star's life and releases a tremendous amount of energy. In a Type Ia supernova, the explosion occurs when a white dwarf reaches the Chandrasekhar limit. The runaway thermonuclear reaction ignites, causing the star to blow apart. The energy released during the explosion is equivalent to the energy output of billions of suns. This energy is unleashed in a matter of seconds, creating an incredibly bright and powerful event. As the supernova explodes, it ejects material at velocities of up to 10,000 kilometers per second. This material expands outward, forming a rapidly growing shell of debris. The light from the explosion travels across the universe, making supernovas visible from great distances. Type Ia supernovas are often used as standard candles to measure cosmic distances due to their consistent luminosity. In the case of a core collapse supernova, the explosion is triggered by the collapse of the star's core. When the core's pressure exceeds its ability to support itself, it collapses, and a shock wave is generated. This shock wave travels outward, blowing off the star's outer layers. The core collapse also produces a burst of neutrinos, which escape the star almost instantaneously. The remnants of the explosion can be observed for thousands of years as supernova remnants. These remnants are clouds of gas and dust that continue to expand and interact with the surrounding interstellar medium. The explosion also produces a variety of heavy elements, which are dispersed into space. These elements contribute to the chemical enrichment of the galaxy and are essential for the formation of new stars and planets. The final explosion can leave behind a dense remnant, such as a neutron star or a black hole. These remnants are the collapsed cores of the original star and have incredibly strong gravitational fields. Neutron stars are incredibly dense, with masses comparable to the Sun but diameters of only about 20 kilometers. They can spin rapidly and emit beams of radiation, observed as pulsars. Black holes formed from the most massive stars have gravitational fields so strong that not even light can escape. They can grow by accreting material from their surroundings, further influencing their environment. The energy and shock waves from the explosion can trigger the formation of new stars by compressing nearby gas clouds. This process contributes to the ongoing cycle of star birth and death in galaxies. Supernova explosions are also significant for their role in cosmic ray production. The shock waves accelerate particles to near-light speeds, contributing to the high-energy particle population in the galaxy. The study of supernova explosions helps astronomers understand the life cycles of stars, the dynamics of galaxies, and the evolution of the universe. Each supernova provides valuable data that enhances our knowledge of these powerful events. Neutrino production is a key aspect of the core collapse supernova process. During the collapse of a massive star's core, immense pressures and temperatures cause protons and electrons to merge, forming neutrons. This process, known as neutronization, releases a flood of neutrinos. Neutrinos are nearly massless particles that interact weakly with matter, allowing them to escape the dense core of the collapsing star. Neutrino production occurs within milliseconds of the core collapse, making neutrinos one of the earliest detectable signals of a supernova explosion. The enormous number of neutrinos produced during a core collapse supernova carries away a significant fraction of the core's gravitational energy. This loss of energy contributes to the rapid collapse of the core and the subsequent rebound shock wave. Neutrinos are generated through various processes during a core collapse supernova. Electron capture, neutronization, and beta decay are among the most important mechanisms responsible for neutrino production. As the shock wave propagates outward through the star's layers, it encounters the dense neutrino-driven wind generated by the collapsing core. This interaction further accelerates the shock wave and enhances the supernova explosion. The neutrinos produced during a core collapse supernova are detected on Earth as a burst of high-energy particles. Neutrino observatories around the world are designed to detect these elusive particles and study their properties. Neutrino detection provides valuable insights into the dynamics and energetics of supernova explosions. By analyzing the neutrino signal, astronomers can infer details about the core collapse process and the mechanisms driving the explosion. The detection of neutrinos from a supernova explosion provides an early warning of the event. Neutrinos travel through space almost unhindered, allowing astronomers to observe the supernova before its light reaches Earth. Neutrinos emitted during a core collapse supernova carry information about the conditions inside the collapsing star. By studying the neutrino signal, scientists can learn about the temperature, density, and composition of the core. The neutrino flux from a supernova explosion is immense, with trillions of neutrinos emitted in just a few seconds. Despite their weak interactions, the sheer number of neutrinos makes them detectable by sensitive instruments. Neutrinos from a core collapse supernova interact with matter in neutrino detectors, producing detectable signals such as flashes of light or tiny bursts of electrons. These signals are used to identify and study neutrino events. The detection of neutrinos from a supernova explosion provides a unique opportunity to study fundamental particle physics in extreme astrophysical environments. Neutrinos offer insights into the behavior of matter under extreme conditions. Neutrino observations complement other observational techniques used to study supernova, such as optical, radio, and X-ray observations. Together, these observations provide a comprehensive understanding of supernova explosions. Neutrino production is a crucial aspect of core collapse supernova, influencing the dynamics, energetics, and observational signatures of these dramatic cosmic events. By studying neutrinos, astronomers gain valuable insights into the inner workings of massive stars and the mechanisms driving their explosive deaths. Neutrino detection is a remarkable feat of modern astrophysics. Neutrinos are incredibly elusive particles, interacting only weakly with matter, making their detection challenging. Despite their weak interactions, neutrinos can be detected using specialized detectors designed to capture the rare interactions that occur. These detectors are typically located deep underground to shield them from cosmic rays and other sources of background noise. Neutrino detection relies on the interaction of neutrinos with atoms in the detector material. When a neutrino collides with an atom, it produces detectable signals such as flashes of light or tiny bursts of particles. Various types of detectors are used to detect neutrinos, including water Cherenkov detectors, liquid scintillator detectors, and noble gas detectors. Each type of detector has its advantages and limitations, depending on the specific scientific goals. Water Cherenkov detectors, such as Super Kamiokande in Japan, use large volumes of water as the detection medium. When a neutrino interacts with the water, it produces Cherenkov radiation, which is detected by photomultiplier tubes. Liquid scintillator detectors, like the CAMLAND experiment, use organic liquids that emit light when a neutrino interacts with them. The emitted light is detected by photomultiplier tubes surrounding the detector. Noble gas detectors, such as those used in the SNO+ experiment, utilize gases like argon or xenon as the detection medium. When a neutrino interacts with the gas, it produces ionization or scintillation signals that are detected by sensitive instruments. Neutrino detection experiments are often conducted deep underground to shield the detectors from cosmic ray background noise. Underground locations, such as mines or tunnels, provide the necessary shielding to reduce unwanted signals. Neutrino detection experiments are conducted in collaboration with scientists and institutions around the world. International cooperation allows researchers to pool resources, expertise, and data to achieve their scientific goals. Neutrino detection plays a crucial role in various fields of astrophysics, including the study of supernovae, neutrino oscillations, and the search for dark matter. Neutrinos provide unique insights into the universe's most extreme environments and phenomena. The detection of neutrinos from astrophysical sources like supernovae provides valuable information about the processes occurring inside these cosmic explosions. Neutrino signals offer insights into the dynamics, energetics, and composition of supernovae. Neutrino detection experiments are continuously improving in sensitivity and precision, allowing scientists to detect increasingly faint signals and study neutrinos in greater detail. Advances in detector technology and data analysis techniques drive progress in the field. Neutrino detection is not only used for astrophysical research, but also has applications in particle physics, nuclear physics, and fundamental physics. Neutrinos are fundamental particles that play a crucial role in our understanding of the universe. The study of neutrinos and their detection is a collaborative effort involving physicists, engineers, and technologists from diverse backgrounds. Together, they work to develop innovative techniques and technologies to push the boundaries of neutrino research. Neutrino detection experiments often involve large international collaborations, with scientists from multiple countries working together to design, build, and operate the detectors. These collaborations foster exchange of ideas and expertise, driving progress in the field. In summary, neutrino detection is a remarkable achievement of modern science, allowing scientists to study some of the universe's most elusive particles and phenomena. By detecting neutrinos, researchers gain unique insights into the inner workings of stars, the dynamics of supernovae, and the fundamental properties of matter. Energy transfer during a supernova explosion is a complex and dynamic process. It involves the conversion of gravitational potential energy from the collapsing core into kinetic energy, thermal energy, and radiant energy. As the core collapses, gravitational potential energy is converted into kinetic energy, causing the core to heat up and increase in density. This process releases a tremendous amount of energy, driving the core collapse and subsequent explosion. The shock wave generated by the collapsing core carries a significant portion of the released energy outward through the star's layers. This shock wave transfers energy to the surrounding material, heating and accelerating it. Energy transfer during a supernova explosion also involves the production and emission of radiation, including visible light, X-rays, and gamma rays. These forms of radiant energy carry away a portion of the released energy, contributing to the brightness of the supernova. Neutrinos play a crucial role in energy transfer during a supernova explosion. Produced in vast quantities during the core collapse, neutrinos carry away a significant fraction of the core's gravitational energy, helping to drive the explosion. The energy carried by neutrinos is released deep within the collapsing core, where temperatures and densities are extreme. Neutrinos escape the core almost unhindered, carrying valuable information about the conditions inside the star. As the shock wave propagates outward through the star's layers, it transfers energy to the surrounding material through various interactions. These interactions include heating, compression, and the generation of secondary shock waves. Energy transfer during a supernova explosion is not uniform throughout the star. The inner regions, closer to the collapsing core, experience higher temperatures and densities, leading to more intense energy transfer processes. The outer layers of the star also undergo significant energy transfer, as they are heated and accelerated by the shock wave. This heating causes the outer layers to expand rapidly, contributing to the supernova's luminosity. The energy transferred during a supernova explosion drives the ejection of material from the star into space. This ejected material, rich in heavy elements synthesized during the explosion, enriches the interstellar medium with new elements. Energy transfer during a supernova explosion influences the appearance and evolution of the resulting supernova remnant. The distribution of energy throughout the remnant determines its morphology, dynamics, and observable properties. Observations of energy transfer during supernova explosions provide valuable insights into the underlying physics of these cosmic events. By studying the distribution and mechanisms of energy transfer, astronomers can better understand the processes driving supernova explosions. The study of energy transfer during supernova explosions is interdisciplinary, involving astrophysicists, nuclear physicists, and particle physicists. Collaborative efforts among researchers from different fields are essential for advancing our understanding of these complex phenomena. Advanced telescopes and observational techniques allow astronomers to study energy transfer in supernovae in unprecedented detail. High-resolution imaging, spectroscopy, and multi-wavelength observations provide valuable data on the distribution and dynamics of energy transfer processes. In summary, energy transfer during a supernova explosion is a multifaceted process that involves the conversion, distribution, and emission of vast amounts of energy. By studying energy transfer in supernovae, scientists gain insights into the inner workings of these dramatic cosmic events and their impact on the universe. The impact of energy transfer on supernova mechanics is profound, shaping the dynamics and evolution of these cosmic explosions. Energy transfer processes, such as shockwave propagation and neutrino emission, drive the expansion and heating of the supernova ejecta, influencing the overall evolution of the explosion. The distribution and magnitude of energy transfer determine the luminosity, duration, and spectral characteristics of the supernova, providing valuable information about the underlying physics of the explosion. Energy transfer also affects the morphology and dynamics of the supernova remnant, shaping its appearance and evolution over time. The interaction between the expanding ejecta and the surrounding interstellar medium is influenced by energy transfer processes. The efficiency of energy transfer mechanisms, such as neutrino emission and shockwave propagation, directly impacts the overall energetics of the supernova explosion. Variations in energy transfer efficiency can lead to differences in the brightness and duration of supernovae. Energy transfer plays a crucial role in determining the fate of the progenitor star and the nature of the compact remnant left behind after the supernova explosion. The amount of energy transferred influences whether the remnant becomes a neutron star or a black hole. Observations of energy transfer in supernova provide valuable constraints on theoretical models and simulations of supernova mechanics. By comparing observational data with theoretical predictions, scientists can refine their understanding of the processes driving supernova explosions. The study of energy transfer in supernova is interdisciplinary, involving astrophysicists, nuclear physicists, and particle physicists. Collaborative efforts among researchers from different fields are essential for advancing our understanding of these complex phenomena. Advanced computational models and simulations allow scientists to study energy transfer in supernova in unprecedented detail. High-resolution simulations provide insights into the dynamics and distribution of energy transfer processes. Energy transfer in supernovae is also influenced by factors such as progenitor mass, metallicity, and rotation. Variations in these parameters can affect the efficiency and distribution of energy transfer mechanisms. The impact of energy transfer on supernova mechanics extends beyond the explosion itself, influencing the chemical enrichment of the interstellar medium and the formation of new stars and planets. Energy transfer processes in supernovae can also trigger secondary phenomena, such as gamma-ray bursts and kilonovae, which have their own unique observational signatures and astrophysical implications. Studying the impact of energy transfer on supernova mechanics provides valuable insights into the processes governing stellar evolution and the dynamics of the universe on cosmic scales. The interplay between energy transfer mechanisms such as shockwave propagation, neutrino emission, and radiation transport is complex and dynamic, requiring sophisticated theoretical models and observational techniques to fully understand. In summary, energy transfer plays a crucial role in shaping the mechanics of supernova explosions, influencing their brightness, duration, and spectral characteristics. By studying energy transfer in supernovae, scientists gain insights into the underlying physics of these cosmic events and their impact on the evolution of the universe. The importance of studying energy transfer in supernovae cannot be overstated. It provides crucial insights into the fundamental processes governing stellar evolution and the dynamics of the universe. By understanding energy transfer mechanisms, scientists can better interpret observational data and refine theoretical models of supernova explosions. This improves our ability to predict and explain the diverse range of supernova phenomena observed in the universe. Energy transfer research also has broader implications for astrophysics, particle physics, and cosmology. It contributes to our understanding of the origin of elements, the formation of galaxies, and the evolution of the universe over cosmic timescales. Studying energy transfer in supernovae helps address fundamental questions about the nature of matter, the behavior of extreme environments, and the role of supernovae in cosmic evolution. Energy transfer research is interdisciplinary, drawing on expertise from various fields, including astronomy, physics, and computational science. Collaborative efforts among researchers with diverse backgrounds are essential for advancing our understanding of these complex phenomena. Advanced observational techniques, such as multi-wavelength imaging and spectroscopy, allow astronomers to study energy transfer in supernovae with unprecedented detail and precision. Theoretical models and simulations play a crucial role in energy transfer research, providing insights into the underlying physics of supernova explosions and the dynamics of stellar evolution. Energy transfer studies are not only driven by curiosity about the universe, but also have practical applications, such as improving our understanding of nuclear reactions, particle interactions, and astrophysical phenomena. By studying energy transfer in supernovae, scientists can test and refine our understanding of fundamental physical processes, such as nuclear fusion, radiative transfer, and gravitational collapse. Energy transfer research also has implications for our understanding of the cosmic microwave background, dark matter, and the large-scale structure of the universe. Understanding energy transfer in supernovae is essential for interpreting observational data from current and future astronomical surveys and telescopes, such as the James Webb Space Telescope and the Vera C. Rubin Observatory. Energy transfer studies contribute to the broader scientific effort to explore the origins and evolution of the universe, addressing fundamental questions about the nature of space, time, and matter. By advancing our understanding of energy transfer in supernovae, scientists can unlock new insights into the mechanisms driving cosmic explosions, the formation of heavy elements, and the evolution of galaxies and clusters of galaxies. Energy transfer research also has practical implications for space exploration, nuclear energy, and national security, as it helps us understand the behavior of matter and energy in extreme environments. In summary, energy transfer studies in supernovae are of paramount importance for advancing our understanding of the universe, from its smallest building blocks to its largest structures. By studying energy transfer processes, scientists gain valuable insights into the fundamental physics that govern the cosmos and our place within it. Nucleosynthesis in stars is the process by which lighter elements are fused together to form heavier elements, releasing energy in the form of radiation. The core of a star serves as a nuclear reactor, where fusion reactions occur under extreme temperature and pressure conditions. Hydrogen fusion, primarily through the proton-proton chain or CNO cycle, produces helium in the core of stars like the Sun, releasing energy in the form of gamma rays and neutrinos. As a star evolves and exhausts its hydrogen fuel, it progresses to more advanced stages of nucleosynthesis, involving the fusion of helium, carbon, oxygen, and heavier elements. Helium fusion, through the triple alpha process, results in the production of carbon and oxygen in the cores of stars with sufficient mass, such as red giants and supergiants. Carbon fusion, occurring at higher temperatures and pressures, leads to the formation of heavier elements such as neon, magnesium, and silicon in the cores of massive stars. Oxygen fusion, which occurs in the later stages of stellar evolution, produces elements such as sulfur, phosphorus, and calcium, contributing to the enrichment of the star's outer layers and eventual ejection into space. During the final stages of stellar evolution, fusion reactions in the core can no longer sustain the star against gravitational collapse, leading to a supernova explosion. The explosive nucleosynthesis during a supernova event generates a vast array of elements heavier than iron, including nickel, cobalt, and a variety of radioactive isotopes. The extreme conditions of a supernova explosion, such as high temperatures, pressures, and densities, facilitate the rapid fusion of lighter elements into heavier elements through processes like the R process and S process. The R process, or rapid neutron capture process, occurs in the explosive environment of a supernova, where neutron-rich nuclei rapidly capture additional neutrons to form heavier elements. The S process, or slow neutron capture process, occurs in the convective shells of evolved stars, where neutrons are captured slowly over long periods, resulting in the gradual production of heavier elements. The nucleosynthesis processes in stars and supernovae play a crucial role in the enrichment of the interstellar medium with heavy elements, which are essential for the formation of planets, moons, and life as we know it. The distribution of elements in the universe reflects the contributions of different nucleosynthesis processes, occurring in stars of various masses and evolutionary stages. Observations of elemental abundances in stars, galaxies, and interstellar gas clouds provide valuable insights into the nucleosynthesis processes responsible for producing the elements we observe. In summary, nucleosynthesis in stars and supernova is a fundamental process that shapes the chemical composition of the universe, leading to the formation of diverse elements and enriching cosmic environments with heavy elements essential for the emergence of life. Supernovae are cosmic furnaces that produce and distribute a wide range of chemical elements, enriching the interstellar medium with heavy elements essential for the formation of planets, stars, and life. The explosive nucleosynthesis during a supernova event generates elements through fusion, neutron capture, and radioactive decay processes. The core collapse and subsequent explosion of a massive star releases enormous amounts of energy, creating conditions for nuclear reactions to occur and elements to be synthesized. The extreme temperatures and pressures during a supernova explosion facilitate the fusion of lighter elements into heavier elements, such as carbon, oxygen, silicon, and iron. Elements heavier than iron, such as nickel, cobalt, and various radioactive isotopes, are predominantly produced through rapid neutron capture processes during the intense conditions of a supernova explosion. The neutron-rich environment of a supernova allows for rapid neutron capture onto existing nuclei, leading to the formation of heavy elements via the R process. The R process involves the rapid addition of neutrons to atomic nuclei, resulting in the synthesis of neutron-rich isotopes with atomic numbers higher than iron. The S process, or slow neutron capture process, also contributes to element production in supernovae, particularly in the outer layers of massive stars, where neutron capture occurs over longer timescales. The S process involves the capture of neutrons by existing nuclei in the convective shells of evolved stars, leading to the gradual production of heavier elements via neutron capture and beta decay. The radioactive decay of unstable isotopes produced during a supernova explosion contributes to the synthesis of heavy elements and enriches the interstellar medium with radioactive nuclei. The distribution of elements produced in supernovae depends on factors such as the initial composition of the progenitor star, the explosion mechanism, and the dynamics of the supernova event. Observations of elemental abundances in supernova remnants, interstellar gas clouds, and meteorites provide valuable insights into the nucleosynthesis processes occurring in supernova. Isotopic signatures preserved in meteorites and terrestrial rocks offer clues about the nucleosynthetic processes that occurred in supernovae and other astrophysical environments. The chemical composition of stars, planetary systems, and galaxies reflects the contributions of supernovae to the enrichment of cosmic environments with heavy elements. The study of element production in supernovae is crucial for understanding the origin of the chemical elements in the universe and the processes responsible for shaping the cosmic abundance patterns. In summary, supernovae play a central role in the synthesis and distribution of chemical elements, contributing to the chemical evolution of galaxies and the diversity of planetary systems throughout the universe. The distribution of elements in the universe is influenced by a variety of astrophysical processes, including stellar nucleosynthesis, supernova explosions, and galactic chemical evolution. Elements are synthesized in the cores of stars through nuclear fusion reactions, which convert lighter elements into heavier ones over the course of stellar evolution. When massive stars undergo supernova explosions at the end of their lives, they release newly synthesized elements into the surrounding interstellar medium, enriching it with heavy elements. The distribution of elements in the interstellar medium is not uniform, but varies spatially and temporally due to the dynamics of star formation, supernova explosions, and galactic winds. Supernova explosions inject heavy elements, such as carbon, oxygen, and iron, into the interstellar medium, where they mix with existing gas and dust to form new generations of stars and planetary systems. The chemical composition of stars, planetary systems, and galaxies reflects the history of element formation and enrichment in their respective environments. Galactic chemical evolution models describe how the abundances of chemical elements in galaxies change over time as a result of stellar evolution, star formation, and gas recycling processes. The distribution of elements in galaxies is shaped by a combination of factors, including the initial composition of the interstellar medium, the rate of star formation, and the efficiency of supernova feedback. Observations of elemental abundances in stars, gas clouds, and galaxies provide valuable constraints on galactic chemical evolution models and our understanding of the origins of cosmic elements. The Milky Way galaxy exhibits a gradient in elemental abundances, with higher concentrations of heavy elements towards the galactic center and lower concentrations in the outer regions. Galactic mergers and interactions can also affect the distribution of elements in galaxies by triggering intense episodes of star formation and redistributing gas and dust across galactic scales. In addition to stars and galaxies, the distribution of elements is also influenced by processes such as cosmic ray spallation, which produces secondary elements through the interaction of high-energy particles with interstellar gas. Observations of elemental abundances in distant galaxies and the intergalactic medium provide insights into the chemical enrichment history of the universe and the evolution of cosmic structures over cosmic time. The distribution of elements in the universe reflects the complex interplay between astrophysical processes, including stellar nucleosynthesis, supernova explosions, and galactic dynamics. Understanding the distribution of elements in the universe is essential for unraveling the cosmic origins of chemical elements, tracing the evolution of galaxies, and deciphering the interconnectedness of cosmic structures across cosmic scales. Supernovae have a profound impact on the interstellar medium, shaping its composition, dynamics, and evolution over cosmic timescales. The intense radiation and shock waves produced by supernova explosions heat and compress the surrounding interstellar gas, triggering the formation of new stars and planetary systems. Supernova remnants, the expanding shells of gas and dust left behind by supernova explosions, inject energy and momentum into the interstellar medium, driving turbulence and promoting the mixing of different gas phases. The shock waves generated by supernova explosions can trigger the onset of star formation by compressing nearby gas clouds and overcoming their gravitational binding energy. Supernova explosions also inject heavy elements, such as carbon, oxygen, and iron, into the interstellar medium, enriching it with the raw materials necessary for the formation of planets, moons, and life. The injection of heavy elements by supernovae contributes to the chemical enrichment of the interstellar medium, increasing its metallicity and altering its chemical composition over time. The energy and momentum deposited by supernovae into the interstellar medium can drive large-scale galactic outflows, expelling gas and dust from galaxies into the intergalactic medium. Supernova-driven outflows play a crucial role in regulating the star formation rate and gas content of galaxies, shaping their morphological and evolutionary properties. The shock waves produced by supernovae can trigger the formation of molecular clouds, dense regions of gas and dust, where new generations of stars are born. Supernova explosions can also disrupt existing molecular clouds, dispersing their gas and triggering the onset of new star formation episodes. The energy and momentum injected by supernovae into the interstellar medium can drive large-scale galactic winds, expelling gas and dust from galaxies into the intergalactic medium. Supernova-driven galactic winds play a crucial role in regulating the chemical enrichment and metallicity of galaxies, as well as their morphological and evolutionary properties. The interaction between supernova-driven shocks and the interstellar medium can produce complex structures, such as supernova remnants, superbubbles, and filaments, which are observed at various wavelengths. Supernovae also contribute to the ionization and heating of the interstellar medium, influencing its physical state and emission properties. Overall, supernovae have a profound and multifaceted impact on the interstellar medium, shaping its dynamics, chemistry, and evolution across cosmic scales. Supernovae play a crucial role in the chemical enrichment of the universe, including our own Milky Way galaxy, which has provided the raw materials necessary for the formation of planets, moons, and ultimately life. The heavy elements synthesized in supernova explosions such as carbon, oxygen, nitrogen, and iron are essential building blocks for the formation of organic molecules, including those involved in the chemistry of life. The Earth and other rocky planets in our solar system contain elements that were forged in the fiery cores of massive stars and dispersed into space by supernova explosions billions of years ago. The presence of heavy elements on Earth, including those essential for life such as carbon, nitrogen, and oxygen, is a direct result of the chemical enrichment processes driven by supernova. The carbon-based molecules that form the basis of life on Earth, including DNA, proteins, and carbohydrates, owe their existence to the synthesis of carbon in the cores of stars and its subsequent dispersion into the interstellar medium. Elements such as oxygen and nitrogen, which are vital for respiration and the formation of organic compounds, were also produced in the nuclear furnaces of massive stars and distributed throughout the galaxy by supernovae. The iron in the Earth's core, which generates our planet's magnetic field and provides stability to its geophysical processes, originated in the cores of massive stars and was dispersed into space by supernova explosions. Supernovae also play a role in the formation of complex molecules, including those found in comets, asteroids, and the interstellar medium, which may have contributed to the origin of life on Earth through processes such as panspermia. The energy released by supernova explosions can trigger shock waves and radiation bursts that may have influenced the formation and evolution of planetary systems, including our own solar system. The radioactive isotopes produced in supernova explosions, such as aluminum-26 and iron-60, may have contributed to the heating and differentiation of planetary bodies and played a role in shaping their geophysical and geochemical properties. The timing and intensity of supernova explosions in our galaxy's history may have influenced the habitability of Earth and other planets, affecting factors such as climate, atmospheric composition, and the availability of essential elements. Supernova remnants, the expanding shells of gas and dust left behind by supernova explosions, can trigger the formation of new stars and planetary systems through the compression and collapse of nearby gas clouds. The chemical composition of meteorites, comets, and interplanetary dust particles provides clues about the role of supernovae in the formation and evolution of our solar system and the delivery of extraterrestrial material to Earth. Studying the isotopic signatures and elemental abundances in meteorites and terrestrial rocks can help scientists trace the origins of the elements in our solar system and understand the processes that shaped its formation. In summary, supernovae have played a vital role in the evolution of the universe and the development of life on Earth, contributing to the chemical enrichment of galaxies, the formation of planetary systems, and the synthesis of the elements essential for life as we know it. Supernovae are relatively rare events in the Milky Way galaxy, with only a few occurring every century on average. Despite their rarity, supernovae have had a significant impact on the evolution of the Milky Way and the distribution of elements within it. Observations of supernova remnants in the Milky Way provide valuable insights into the mechanisms of supernova explosions and their effects on the interstellar medium. The Milky Way has experienced numerous supernova events throughout its history, contributing to the chemical enrichment of its interstellar medium and the formation of new generations of stars. Historical records and archaeological evidence suggest that several supernova explosions have been observed from Earth over the past millennia, including the famous SN 1054, which resulted in the Crab Nebula. Recent surveys and observations have identified several candidate supernova progenitor stars in the Milky Way, providing valuable information about the types of stars that can undergo supernova explosions. Studying the distribution and properties of supernova remnants in the Milky Way helps astronomers understand the rates and mechanisms of supernova explosions in our galaxy. Supernovae in the Milky Way can have far-reaching effects on the surrounding interstellar medium, triggering the formation of new stars and influencing the chemical composition of gas clouds and dust. The study of supernovae in the Milky Way is essential for understanding the life cycle of stars, the production of heavy elements, and the dynamics of galactic evolution. Supernovae in the Milky Way are often classified based on their observational properties, such as their light curves, spectra, and associated remnant structures. Recent advances in observational techniques, such as high-resolution imaging and spectroscopy, have enabled astronomers to study supernovae in unprecedented detail in the Milky Way. The study of Milky Way supernova is also important for understanding the potential impact of these events on Earth and other planets in our solar system. Future surveys and observational campaigns, such as those conducted by next-generation telescopes and space missions, will continue to advance our understanding of supernovae in the Milky Way. The study of Milky Way supernovae is also important for understanding the dynamics and evolution of our galaxy, including its star formation history and chemical enrichment processes. In summary, supernovae in the Milky Way play a crucial role in shaping the galactic environment, influencing the formation of stars and planetary systems, and enriching the interstellar medium with heavy elements. Supernovae in distant galaxies provide valuable insights into the early universe and the processes that shaped its evolution. Observations of supernovae in distant galaxies help astronomers understand the star formation history, chemical enrichment, and dynamics of galaxies across cosmic time. Studying supernovae in distant galaxies allows astronomers to probe the properties of galaxies at different epochs and trace their evolutionary paths. Distant supernovae serve as cosmological probes, providing constraints on the expansion history of the universe and the nature of dark energy. The study of supernovae in distant galaxies has led to groundbreaking discoveries such as the accelerated expansion of the universe and the existence of dark energy. Distant supernovae are often classified based on their redshifts, which provide information about their distances and the cosmic time at which they occurred. Observational campaigns, such as large-scale surveys and dedicated monitoring programs, have detected and characterized numerous supernovae in distant galaxies. The study of supernovae in distant galaxies requires sophisticated observational techniques, including multi-wavelength imaging, spectroscopy, and time-domain astronomy. Supernovae in distant galaxies exhibit a diverse range of properties, reflecting the diversity of their progenitor stars and the environments in which they formed. The identification and characterization of supernovae in distant galaxies rely on collaborations between astronomers worldwide and the coordination of observational resources. Distant supernovae provide constraints on the progenitor masses, explosion mechanisms, and nucleosynthesis processes of massive stars in different galactic environments. The study of supernovae in distant galaxies sheds light on the chemical evolution of galaxies, the production of heavy elements, and the feedback processes that regulate star formation. Observations of distant supernovae help astronomers understand the interplay between galaxies, intergalactic medium, and cosmic structures across cosmic time. Supernovae in distant galaxies serve as signposts of cosmic evolution, highlighting the role of stellar processes in shaping the universe's structure and composition. The study of distant supernovae is essential for refining cosmological models, testing theories of galaxy formation and evolution, and unraveling the mysteries of the early universe. Comparative rates of supernova occurrences vary across different types of galaxies, with factors such as stellar populations, metallicity, and star formation activity influencing their frequency. Studies have shown that the rate of supernova explosions is higher in galaxies with active star formation, where young, massive stars are more prevalent. Galaxies with higher gas densities and more extensive star-forming regions tend to experience a higher rate of supernova explosions compared to galaxies with lower star formation activity. The rate of supernova occurrences also depends on the stellar mass and evolutionary stage of the galaxy, with more massive galaxies generally experiencing higher supernova rates due to their larger reservoirs of gas and stars. Dwarf galaxies, which have lower stellar masses and less extensive star formation, tend to have lower supernova rates compared to more massive spiral and elliptical galaxies. The rate of supernova occurrences in a galaxy can also be influenced by its environment, such as its proximity to other galaxies, interactions with companions, and gravitational interactions within galaxy clusters. Comparative studies of supernova rates in different types of galaxies help astronomers understand the factors that govern stellar evolution, star formation, and galaxy dynamics. The observed rates of supernova occurrences in galaxies provide constraints on theoretical models of stellar evolution, supernova progenitors, and the chemical enrichment history of galaxies. Supernova rates in galaxies are often inferred from observational surveys and statistical analyses of large galaxy samples, combined with theoretical predictions and simulations. The study of comparative supernova rates in galaxies requires a multi-wavelength approach, combining data from optical, infrared, radio, and X-ray observations to trace the various stages of stellar evolution and supernova activity. Comparative studies of supernova rates in galaxies also provide insights into the role of environment, feedback processes, and galaxy interactions in shaping the cosmic landscape. Galaxies with higher rates of supernova occurrences may exhibit more pronounced effects of supernova-driven feedback, such as gas expulsion, turbulence, and chemical enrichment. The observed distribution of supernova types and subtypes in galaxies can provide clues about the underlying stellar populations, evolutionary pathways, and physical conditions within galaxies. Comparative studies of supernova rates in galaxies help astronomers investigate the connections between supernova explosions, galaxy evolution, and the cosmic cycle of matter and energy. Understanding the comparative rates of supernova occurrences in galaxies is essential for constraining models of galaxy formation and evolution, stellar feedback processes, and the cosmic history of chemical enrichment. Environmental factors play a crucial role in shaping the occurrence and properties of supernova explosions within galaxies. Galactic environment, including factors such as gas density, metallicity, and gravitational interactions, can influence the formation and evolution of massive stars and their ultimate fate as supernovae. The density and composition of the interstellar medium in galaxies affect the dynamics of star formation, the mass distribution of stellar populations, and the likelihood of supernova explosions. Galaxies with higher gas densities and higher rates of star formation tend to have more massive stars and experience more frequent supernova explosions compared to galaxies with lower gas densities. Metallicity, or the abundance of heavy elements in galaxies, can impact the formation and evolution of massive stars, affecting their mass loss rates, stellar winds, and eventual supernova progenitors. Low metallicity environments, such as those found in dwarf galaxies and the early universe, may favor the formation of massive stars with higher masses and higher rates of supernova explosions. Galactic interactions, such as mergers, interactions with companions, and tidal forces within galaxy clusters, can trigger enhanced star formation activity and increase the rates of supernova occurrences. The presence of dense gas clouds, spiral arms, and regions of active star formation within galaxies can create favorable conditions for the formation of massive stars and their eventual supernova explosions. Supernova explosions can also be influenced by the presence of binary star systems, which can lead to mass transfer, mergers, and the formation of supernova progenitors with specific properties. Galactic environments with higher stellar densities and more complex gravitational potentials may experience different types of supernova explosions, such as core collapse supernova and type I supernovae, compared to isolated galaxies. The dynamics of supernova explosions within galaxies can affect the chemical enrichment history, energy budget, and morphological evolution of galaxies over cosmic time. The interplay between environmental factors, such as gas dynamics, turbulence, and magnetic fields, can influence the progenitor conditions, explosion mechanisms, and observable properties of supernovae. Comparative studies of supernova environments in different types of galaxies help astronomers understand the role of environmental factors in shaping the cosmic distribution of supernovae. Observational surveys and numerical simulations of galaxy formation and evolution provide valuable insights into the connections between environmental factors, supernova occurrences, and galactic dynamics. Understanding the influence of environmental factors on supernova explosions is essential for interpreting observational data, constraining theoretical models, and unraveling the complex interplay between stars, galaxies, and the cosmic environment. The formation of neutron stars is one of the possible outcomes of supernova explosions, particularly in core collapse supernova. During a supernova explosion, the core of a massive star undergoes rapid gravitational collapse, leading to the formation of a dense, compact remnant known as a neutron star. The collapse of the stellar core compresses protons and electrons together to form neutrons, resulting in a highly dense and compact object composed primarily of neutrons. Neutron stars are incredibly dense, with densities exceeding that of atomic nuclei, and they typically have masses several times that of the Sun, but sizes comparable to a city. The intense gravitational forces in the vicinity of a neutron star give rise to extreme conditions, including strong magnetic fields, high temperatures, and intense radiation. Neutron stars often possess rapid rotational velocities, with some spinning hundreds of times per second, due to the conservation of angular momentum during the collapse process. The formation of neutron stars is associated with the release of enormous amounts of energy, which powers the supernova explosion and produces the observed luminosity and kinetic energy. Neutron stars can emit radiation across the electromagnetic spectrum, from radio waves to gamma rays, and their emissions can vary over time due to processes such as pulsations, accretion, and magnetic interactions. The intense magnetic fields of neutron stars can give rise to phenomena such as pulsars, magnetars, and X-ray binaries, which emit periodic pulses of radiation and exhibit variability in their emission properties. Neutron stars are also sources of gravitational waves, particularly during their formation through core collapse supernova and during subsequent interactions with companions or surrounding matter. The study of neutron stars provides valuable insights into the physics of extreme environments, including the behavior of matter under extreme pressures, temperatures, and magnetic fields. Observations of neutron stars in various astrophysical contexts, such as supernova remnants, pulsar wind nebulae, and binary systems, help astronomers understand their formation mechanisms and evolutionary pathways. Neutron stars play a crucial role in the chemical enrichment of the interstellar medium, as they produce and eject heavy elements synthesized during the supernova explosion. The study of neutron stars also has implications for fundamental physics, including tests of general relativity, the equation of state of dense matter, and the nature of exotic particles and interactions. In summary, the formation of neutron stars through supernova explosions represents one of the most extreme and fascinating phenomena in astrophysics, offering insights into the nature of matter, gravity, and the universe's evolution. Black hole creation is another possible outcome of supernova explosions, particularly in cases where the collapsing stellar core exceeds a critical mass threshold. When the collapsing core of a massive star surpasses the Chandrasekhar limit or the Tolman-Oppenheimer-Volkoff limit, gravitational forces overwhelm all other forces, resulting in the formation of a black hole. Black holes are regions of space-time where gravity is so intense that not even light can escape, leading to the formation of a singularity at the center surrounded by an event horizon. The formation of a black hole during a supernova explosion depends on various factors, including the mass, metallicity, and evolutionary stage of the progenitor star. For a black hole to form, the collapsing stellar core must overcome the pressure support provided by electron degeneracy or nuclear forces, leading to the direct collapse of matter into a singularity. The creation of a black hole is associated with the release of gravitational potential energy, which powers the supernova explosion and drives the ejection of stellar material into space. Black holes come in different sizes, ranging from stellar mass black holes, formed from the remnants of massive stars, to supermassive black holes, found at the centers of galaxies, and weighing millions or even billions of solar masses. Stellar mass black holes typically have masses ranging from a few times that of the Sun to several tens of solar masses, depending on the properties of the progenitor star and the collapse mechanism. The formation of black holes through supernova explosions is crucial for understanding the cosmic distribution of black holes, their properties, and their role in galactic dynamics. Black holes have profound effects on their surrounding environments, influencing the evolution of galaxies, the dynamics of stellar populations, and the formation of exotic astrophysical objects. The study of black hole creation through supernova explosions provides insights into the physics of extreme gravitational collapse, the behavior of matter at high densities, and the nature of space-time curvature. Observational evidence for black hole formation in supernova explosions comes from various sources, including the detection of gravitational waves, X-ray emissions from accretion disks, and the dynamical properties of binary systems. Black hole creation represents one of the most extreme and enigmatic phenomena in astrophysics, offering profound implications for our understanding of the universe's fundamental laws and cosmic evolution. The study of black hole formation through supernova explosions is a thriving area of research, combining observational data, theoretical models, and numerical simulations to unravel the mysteries of black hole physics. In summary, black hole creation through supernova explosions represents a key process in the life cycle of massive stars, shaping the cosmic landscape and offering insights into the nature of space-time, gravity, and the universe's most extreme phenomena. Supernova remnants are the glowing, expanding shells of gas and dust that result from supernova explosions. These remnants contain the ejected material from the supernova explosion, along with shock waves generated by the explosion's energy. Supernova remnants play a crucial role in the life cycle of galaxies, as they enrich the interstellar medium with heavy elements synthesized during the supernova explosion. The expanding shock waves from supernova remnants can trigger new episodes of star formation by compressing nearby gas clouds and triggering gravitational collapse. Supernova remnants are visible across multiple wavelengths of light, from radio waves to X-rays, providing valuable insights into their physical properties and evolutionary stages. Observations of supernova remnants reveal complex structures, including filaments, shocks, and hot gas bubbles, indicative of the dynamic processes at play within these objects. The study of supernova remnants helps astronomers understand the energetics of supernova explosions, the mechanisms of shockwave propagation, and the injection of energy and matter into the interstellar medium. Supernova remnants also serve as laboratories for studying cosmic ray acceleration, as the shock waves within these remnants can accelerate charged particles to high energies. The interaction between supernova remnants and their surrounding environment can lead to the formation of new stars, the disruption of existing stellar systems, and the shaping of galactic structures. Supernova remnants can persist for thousands to millions of years, gradually fading as they disperse their energy and material into the interstellar medium. Some supernova remnants exhibit characteristic emission lines in their spectra, revealing the presence of specific elements such as hydrogen, helium, oxygen, and iron. The morphology and evolution of supernova remnants depend on various factors, including the properties of the progenitor star, the surrounding interstellar medium, and the age of the remnant. Observations of supernova remnants in different stages of evolution provide insights into the processes of shockwave dynamics, radiative cooling, and particle acceleration. Supernova remnants are important sources of energy, matter, and chemical enrichment in galaxies, contributing to the overall evolution and dynamics of the galactic ecosystem. The study of supernova remnants spans multiple disciplines, including astronomy, astrophysics, and plasma physics, offering a rich field for scientific investigation and discovery. Supernovas have a profound impact on the surrounding space, influencing the structure, dynamics, and composition of the interstellar medium. The energy released during a supernova explosion can heat and ionize nearby gas clouds, triggering the formation of shock waves that propagate through the interstellar medium. These shock waves compress gas and dust, leading to the formation of new stars and stellar systems in regions where star formation was previously dormant. Supernovas inject heavy elements synthesized in their cores into the surrounding space, enriching the interstellar medium with elements crucial for the formation of future generations of stars and planetary systems. The shock waves generated by supernova explosions can disrupt nearby molecular clouds, triggering the collapse of gas and dust into new star-forming regions. Supernova remnants expand rapidly into the interstellar medium, sweeping up and compressing surrounding material as they propagate through space. The interaction between supernova remnants and the interstellar medium drives turbulent motions, mixing and chemical enrichment within the galaxy. Supernova explosions can create cavities or bubbles in the interstellar medium, carving out regions of low-density gas and influencing the overall structure of the galaxy. The energy and momentum transferred from supernova explosions to the interstellar medium can drive galactic outflows, expelling gas and dust from the galaxy into the intergalactic medium. The shock waves and radiation from supernovas can trigger the formation of massive stars in regions of high-density gas, leading to the creation of stellar clusters and associations. Supernova explosions can stir up the interstellar medium, redistributing matter and energy throughout the galaxy and affecting the formation and evolution of future generations of stars. The impact of supernovas on surrounding space is not limited to their immediate vicinity, but can extend over large distances, influencing the structure and dynamics of the entire galaxy. Supernovas play a crucial role in galactic evolution, shaping the distribution of gas, stars, and dark matter within galaxies over cosmic timescales. The energy released by supernova explosions can drive large-scale galactic winds, expelling gas from the central regions of galaxies and regulating star formation activity. The chemical enrichment produced by supernova explosions contributes to the diversity of elements observed in galaxies, influencing the properties of stars, planets, and other celestial bodies. The long-term effects of supernovas extend far beyond their initial explosion, shaping the evolutionary trajectory of galaxies over billions of years. Supernova explosions inject energy, matter, and heavy elements into the interstellar medium, influencing the dynamics of gas clouds and the formation of new stars. The chemical enrichment produced by supernovas alters the composition of the interstellar medium, enriching it with elements essential for the formation of planets, moons, and other celestial bodies. The energy released during supernova explosions can drive galactic outflows, expelling gas and dust from the central regions of galaxies and regulating star formation activity. Supernova remnants serve as sites of ongoing star formation, as the shock waves and turbulence they generate can trigger the collapse of nearby gas clouds into new stellar systems. The remnants of massive stars that have undergone supernova explosions can evolve into neutron stars or black holes, influencing the dynamics of their surrounding environments. The gravitational influence of supernova remnants can shape the orbits of nearby stars and planetary systems, leading to changes in the structure and stability of galactic disks. The energy deposited by supernovas can heat and ionize the interstellar medium, creating ionized bubbles and filaments that are observable across multiple wavelengths of light. Supernova explosions contribute to the dispersal of heavy elements throughout galaxies, enriching the galactic environment and providing the raw materials for future generations of stars and planetary systems. The shock waves generated by supernovas can trigger the formation of molecular clouds, fostering the conditions for the birth of new stars and planetary systems. The long-term effects of supernovas on galactic evolution depend on various factors, including the mass and metallicity of the progenitor star, the surrounding interstellar environment, and the galactic dynamics. Supernova explosions can disrupt the orbits of nearby stars, leading to close encounters, mergers, or ejections from the galaxy, altering the stellar population and distribution. The chemical enrichment produced by supernovas influences the composition of stars and planetary systems formed after the explosion, leaving a lasting imprint on their properties and evolution. The energy and momentum injected into the interstellar medium by supernovas can drive large-scale galactic winds, affecting the circulation of gas and the formation of structures within galaxies. Supernova explosions contribute to the overall energy budget of galaxies, influencing their gravitational potential, dynamical evolution, and interactions with neighboring galaxies. Throughout this video, we've delved into the fascinating realm of supernovas, exploring their diverse types, mechanisms, and impacts on the cosmos. We began by defining what supernovas are and delving into their historical significance, highlighting their pivotal role in shaping our understanding of the universe. From their importance in astronomy to their various subcategories and comparison of types, we've examined the intricate processes that lead to these spectacular cosmic explosions. We've journeyed through stellar formation, main sequence phases, and the dramatic transformations that occur during a star's life cycle, leading to core collapse and eventual explosion. We've also discussed the critical role of supernovas in nucleosynthesis, element production, and their profound influence on the interstellar medium and surrounding space. Our exploration has extended beyond the observational realm, delving into computational simulations, theoretical frameworks, and predictive models that deepen our understanding of supernova dynamics. Recent advances in observational techniques, computational astrophysics, and interdisciplinary collaborations have propelled the field forward, unveiling new insights into supernova physics and unveiling exotic phenomena. From neutron star formation to black hole creation, supernova remnants and their long-term effects, we've traversed a vast cosmic landscape teeming with wonder and discovery. As we conclude our journey, I encourage you to reflect on the awe-inspiring complexity and beauty of supernovas, which serve as cosmic crucibles for the creation of elements and the evolution of galaxies. If you've enjoyed this exploration of supernovas and want to continue learning about the wonders of the universe, I invite you to like and subscribe to our channel. By doing so, you'll stay updated on our latest videos covering a wide range of topics in astronomy and astrophysics. Thank you for joining us on this cosmic voyage, and we look forward to sharing more exciting discoveries with you in the future. Until next time, keep looking up at the stars.